Hey guys, hope everybody's doing all right. I wanted to make a quick video that went along with the post-lab analysis for the Beers Law percent copper and brass lab. So if you're working on those post-lab questions and you're having an issue or you're stuck on certain parts, maybe after watching this it'll help out a little bit and you'll feel a little more confident with what you're completing. So a reminder for the lab, we wanted to take our brass pieces, we reacted them with nitric acid and we made a copper solution basically. We had a blue solution. So the blue solution tells us there's some concentration of copper in there, right? What we want to do is figure out how much copper is in that actual solution that we made from the brass pieces. We do that through a process called Beer's Law. The example I showed you in class looks like this. You had a test tube with no concentration of your ion in it. Then test tube number 5 had the highest concentration. And these are known. Okay, so I made the calibration curve in this lab. So I made a 0.4 molar copper solution, a 0.2, a 0.1, a 0.05, and a 0 molar. Okay, now this is red, ours were blue, but this is the slide I found. So what we would do is find the absorbance, the known absorbance of this, and this. Plot it, using Google Sheets or graphical analysis. And then we would figure out where on that best fit line, on that calibration curve, is our absorbance from the unknown. Okay, so if you have these two solutions, A and B, the one that's darker is going to absorb more light, right? So the darker solutions have a higher absorbance and the lighter solutions have a lower absorbance at the wavelength that you chose, okay? So we want to pick the wavelength where the absorbance is going to be maximized. We'll talk about that more in a minute. What you'll do is you'll plot those 4 points. So I gave those to you in this lab, okay? If you're doing this lab during a different year where you made those yourselves, you would, again, just take your concentrations that you know of, your 0.4, 0.2, 0.1, 0.05, and then your absorbances from those, plot them. Hopefully you get a nice straight linear line with a good R-squared value. And you're going to have the computer figure out what is the formula for that best fit line for you. Okay? What you'll do then is take your absorbance, pop it into your best fit line equation, find your unknown concentration. So here's the general formula for that. So absorbance equals, there's this like slope value here. This is where your pathway comes in, and some things that you don't really have to worry about in terms of the numbers. And then your concentration, so this is Y equals M, okay, and that's in your pre-lab a little bit. X is your concentration plus B. We talked about your y-intercept here should be at 0 absorbance because you don't have any absorbance at no absorbance with something with 0 concentration, right? If your x value or if your absorbance is 0, okay, your concentration is 0, and then your y-intercept is 0. Okay, so that's what we would have here, and there are some numbers on the slide here. So what you'll do is plot your data, and then you will take your absorbance value and pop it in here for y. Okay, because y is plotted here on the y-axis, or absorbance is here on the y-axis. All right. Your slope comes from your best fit line. Your x is your concentration because it's on the x-axis, and plus b. Now in the lab, you're going to have a little bit of error, so your y-intercept won't be exactly 0. Okay, it should be really, really close to 0 though, or else it'll really throw things off. Okay, so that's what this is summarizing here. Okay, and that's not what you need. Let's take a look at the lab itself really quick, and then we'll go from there. Okay, so here's the lab itself. Pre-lab. Okay, here's the y equals mx plus b information down here. Tells you what this stuff means right there. Pre-lab stuff. And okay, here's part B of the lab that we didn't do, and I really never do this. I have different solutions. I have an iron solution, a zinc solution, and a copper solution. I popped them in the spectrovis to see where that maximum absorbance is located. So an iron chloride solution, or any iron solution, is usually pretty yellowish in color. You can see at the maximum absorbance. This shows up better here because it's in color. Your lab paper is in black and white. You know, the max absorbance is at like 430-ish nanometers in terms of your wavelength. And then it really tails off here, and it's a very low absorbance here later on in the spectrum. Zinc solutions are clear. There's some information about that in your pre-lab as to why, but think about the electron configuration for zinc. And look, its absorbance is 0 all the way through in the visible spectrum. There's a couple lab questions about that. and here is copper. So there's a lot of noise up here. You can't really see it too well, a lot of like jumping around with the absorption. So we're going to go around like 635, 640. Our colorimeter or SpectraVis we used, I collected it at 635 nanometers because you have a pretty good, or about right here-ish, pretty good absorbance right there. Okay, so some questions in your post lab about how these would interfere, or would they or wouldn't they interfere. You want to pick the wavelength where the maximum absorbance is located for that particular substance. So it would make no sense for us to set our wavelength to 500 nanometers for our copper solutions that we made, because look, at 500 nanometers it's zero absorbance. So you'd make all your solutions for your calibration curve. You'd have your brass sample that's diluted or dissolved, and you'd have that sample. You'd put them in, you get 0, 0, 0, 0, 0, right? You get 0 for all those. So you'll make sure you pick the wavelength with the highest absorbance. All right. To wrap it up, we're going to move down here. You'd have here you're going to do a little bit of M1, V1, M2, V2 calculations and solve for your initial volume to make your calibration curve. And here are some of your post-lab questions. I mentioned a few of these as we went through. When you get to 5 and 6, that's when you're going to use your best fit line that hopefully you have made from Google Sheets or graphical analysis. And then you'll just do some mole conversion stuff here once you figure out what your concentration of copper is in your brass sample. So some mole conversion percent stuff here. And then percent error, theory question there. And then finally, for this last part, you have another sample here. So this is just exactly what you did in 5 and 6 earlier in the post lab. So you have another alloy. That's what we had in this lab, was a brass alloy. You have another alloy of nickel and iron. It gives you a calibration curve. Here's your data, 0.2, 0.1, 0.05, 0.025, and 0.010 molar samples. Here's your absorbance. And here's your unknown, 0.3730 for your absorbance of your unknown. Okay, so that's going to be what you're going to use to pop into your best fit line equation here and figure out what your concentration of iron is going to be. So the alloy has to contain 43% nickel, plus or minus 0.5%, so 42.5 to 43.5 nickel. The rest is iron. What you're going to do is use this calibration curve, use this data over here, specifically your unknown sample. You're going to figure out, is this actually 50 whatever percent iron? How accurate is this alloy that you're analyzing? So number 1 here, find the percent iron in the alloy sample as just like what you did up here. Okay, find the percent copper in your brass sample. So 5 and 6 led you to that percent copper. You're going to do all that work with this other example here. Okay, so you'll do the work from 5 and 6, but with the new set of data and best fit line here. Is it acceptable? And a wavelength question I kind of referenced earlier. All right, so that should take care of the post lab for you. If you have any questions, let me know. But hopefully this made a little bit more sense and gave you an opportunity to look at what is going on here. All right, thanks guys.